Okay, for the is this the last talk? I think the last talk for today. Briony, Eldridge, loop spaces are polynomial products associated with polyhedral joint products. It's a long title.
Well, good afternoon, everybody. And firstly, thank you to the organisers for inviting me to speak. It's a real honour to be here. And I never met Fred, but it's been so lovely to hear everybody's stories about him. It's been really... Oh, sorry, I thought it was on. Is this better? Yeah. Can people... Okay, I'll just hold it. Yes, so today I'm going to talk about loop spaces of polyhedral products associated with polyhedral join products. So first, I'm going to go over some preliminary results. I'm going to give some motivation, and I'm going to talk a bit about the combinatorics of the polyhedral join product. Then I'm going to go over my two main results. The first one is giving a homotopy equivalence for the loop spaces of polyhedral products associated with polyhedral join products. And the second result is determining when the loop spaces of these polyhedral products have the homotopy type of a product of spheres and loops on spheres. And then finally, I'm going to use the combinatorics of the polyhedral join product to create new examples of simplicial complexes that produce moment angle complexes that have a loop space homotopy equivalent to a product of spheres and loops on spheres. So to start off, I thought I'd give some motivation. And for that, we turn to Moore's conjecture. So let X be a finite simply connected CW complex. The homotopy exponent of X at a prime P is the least power of P that annihilates the P torsion in the homotopy group of X. The space X is elliptic if it has finitely many rational homotopy groups, and hyperbolic if it has infinitely many rational homotopy groups. Moore's conjecture states that the following are equivalent. X is elliptic, X has finite homotopy exponent at every prime P, and X has finite homotopy exponent at some prime P. So Moore's conjecture is known for some cases. For example, elliptic spaces with finite exponents at all primes, including spheres, finite H spaces with finitely generated cohomology, and odd primary Moore spaces. One strategy for finding if spaces satisfy Moore's conjecture is finding a decomposition for the loop space of X in terms of spaces for which we know the homotopy exponent and rational homotopy groups. So if we let P be the collection of H spaces, which are homotopy equivalent to a finite type product of spheres and loops on simply connected spheres, if the loop space of a space X is in P, then Moore's conjecture holds for X because we know the homotopy exponents for spheres and we know their rational homotopy groups. So we want to look at this for polyhedral products. So what is a polyhedral product? Well, let K be a simplicial complex on the vertex set M, and let X and A be a sequence of pairs of pointed CW complexes. For each face of K, we can define this XA to the sigma as a product YI, where YI is equal to XI if I is in the face sigma, and AI if I is not in the face sigma. And the polyhedral product associated to K is found by taking the union over all the faces of K. So some examples, if we take K to be the full simplex on M vertices, our polyhedral product is going to be the product of all the Xi's. If we take K to be the empty set, we're going to get our polyhedral product is just going to be the product of all the AI's. If we look at a more specific example now, so we're going to let X and A be D2 and S1, which is the moment angle complex and called and often denoted ZK. This is a really significant example of a polyhedral product. So some examples of this is when we take K to be the boundary of an M-1 simplex, our moment angle complex is going to be homotopy equivalent to a sphere of dimension 2M-1. If K is the boundary of a square, then our moment angle complex will be the product of two three-dimensional spheres. And finally, for M greater than or equal to 5, if we take the moment angle complex on the boundary of an M-gon, we get this big connected sum. So you can kind of see from these examples that relatively small changes to the topology of the simplicial complex can produce really quite large changes in the homotopy type of the moment angle complex. So we're looking at when loop spaces of moment angle complexes belong to P, and this is known in various cases. So the first case is when the underlying moment angle complex itself is a wedge of spheres, then by the Hilton-Milnor theorem, we're going to get that loops on that moment angle complex belong to P. This happens, there's loads of known cases for which, for simplicial complexes that produce moment angle complexes belonging to W, for example, flag complexes with chordal 1 skeleton, shifted complexes, and totally fillable complexes. Then if K is the K skeleton of a flag complex, then loops on that moment angle complex belong to P. That's a result of Stanton. If K is a triangulation of S2 or S3, then loops on the moment angle complex belong to P. And if K is a two-dimensional simplicial complex and the homology of the full subcomplexes is torsion-free, then loops on that moment angle complex belong to P. So we want to use the polyhedral join product to create new simplicial complexes outside of this list, such that loops on its moment angle complex belongs to P. So what's a polyhedral join product? Well, it's defined very similarly to the polyhedral product, but instead of the Cartesian product, we're looking at the join product. And this means it's well defined on simplicial complexes. So let M be a simplicial complex on M vertices, and now let K and L be a sequence of pairs of simplicial complexes. For each phase sigma of M, we can define now this KL to the join sigma, which is this join product of YIs, where YI is equal to KI if I is in sigma, and LI if I is not in sigma. And the polyhedral join product is defined by taking the union over all the faces of M. Some examples of that. So to kind of mirror the first two examples of the polyhedral product, if we let M be the full simplex on M vertices, then our polyhedral join product is going to be the join of K1 to Km. Similarly, if we let M be the empty set, then our polyhedral join product is going to be the join of L1 to Lm. Now for some more specific examples. So if we let the pair KL be a vertex and the empty set, we're going to get that our polyhedral join product is actually just the underlying simplicial complex M. And finally, if we let K and L both be vertices, then our polyhedral join product is actually just a full simplex on M vertices. One specific example of polyhedral join products that are very significant in my work is substitution complexes. And this is the case when all of our LIs are just the empty set. So in this case, we call it the substitution complex, and we denote it with this M K1 to Km notation. So here's an example. We're going to let M be the boundary of a two simplex. We're going to let K1 and K2 both just be vertices. And we're going to let K3 be an edge. So you can see here on the left, I've got the simplicial complex M, and on the right, the substitution complex. And you can see why it gets the name substitution complex, because it looks like we have literally substituted the edge in at the vertex 3. Some of you might recall that for any simplicial complex, you can kind of define it as something referred to as the link star restriction push out. So we can write it as a push out of the link and the star over of the star and the restriction over the link. This actually induces a push out on the level of polyhedral join products. So we can write it as this. And we can use this kind of information to, instead of viewing the polyhedral join product as kind of you take M and then produce the polyhedral join product, we can actually do this sequentially. So at each vertex, we can apply this push out to the vertex and slowly build up to our polyhedral join product. And this is quite a useful tool in proving things about polyhedral products associated to polyhedral join products. Finally, to kind of round this section off, I just want to talk about the full subcomplexes of the polyhedral join product. So there are two types of full subcomplexes. The first arises from the full subcomplexes of M. So if we let N be a full subcomplex of M, then the polyhedral join product on N is going to be a full subcomplex of the polyhedral join product on M. And the second come from the full subcomplexes of KIs. So if we let PI denote a full subcomplex of KI, and let QI denote the restriction of LI to the vertex set of PI, then the polyhedral join product on that pair is going to be a full subcomplex of our original polyhedral join product. So some examples of these, and for this we're going to specify to the substitution complex. So as each vertex is a full complex of M, for any simplicial complex, we're going to get that each Ki, because we can write that as a polyhedral joint product on the simplicial complex I on that vertex, is going to be a full subcomplex of our polyhedral joint product. And the second result is if we let all of our PIs just equal a vertex, then we're going to recover that for the substitution complex, M itself is a full subcomplex of the polyhedral joint, well, of the substitution complex. The first result holds for any polyhedral joint products. You're always going to get that these Ki's are full subcomplexes of them, but the second result only holds for the substitution complex. You don't normally recover M as a full subcomplex of a polyhedral joint product. Okay, so I'm going to talk a bit about my main results. So there are two kind of goals for this section. Can we describe loops on the polyhedral product associated with the polyhedral joint product in terms of the component spaces? So M, K, L, and X and A. And the second question is, if we start with something that has a loop space in P, what conditions are needed on our K and L's to ensure that the polyhedral product on the polyhedral joint product stays in P? So to start with, we're going to think about the first question. So this bottom push out here is induced by the push out of the polyhedral joint product, which will induce a push out on the level of polyhedral products. Now there are kind of clear natural maps into this space, which is the polyhedral product and the polyhedral joint product on the restriction, with the polyhedral product on this Km. So here it will be the identity with an inclusion, and here it will be an inclusion with the identity. Because these maps agree here, we're going to get an induced push out map here. And then using the cube lemma, we can lift up and get a homotopy push out of the fibers of these maps. So GM is going to be the homotopy fiber of including LM into KM, and HM is going to be the homotopy fiber of including the polyhedral product on the polyhedral joint product on the link into the polyhedral product on the polyhedral joint product on the restriction. So we then get a homotopy fibration that looks like this, where these maps are as described before, and we can actually show that this homotopy fibration splits to give this homotopy equivalence here. And then if we look at the first term, we can see that this is actually a polyhedral product on a polyhedral joint product. So we can repeat our kind of prior argument, get a loop space homotopy equivalence for that, and substitute it in. So iterating that progress, we obtain our first kind of main result, which is that there is a homotopy equivalence between loops on the polyhedral product associated with the polyhedral joint product, and this product of loops on the polyhedral products associated with the Ki's, and this product here of joins of fibers where GI is defined kind of inductively as the homotopy fiber of including the polyhedral product on the polyhedral joint product of this deleted link into the polyhedral product on the polyhedral joint product of this restriction, and HI is the homotopy fibers of these maps going from the polyhedral product on Li into the polyhedral product on Ki. Okay, so we can use this to show under certain conditions when the polyhedral join operation kind of preserves this property of having a loop space in P. And for this, we're going to consider polyhedral products of the form conon AA, of which the moment angle complex is an example of. So here's the second theorem. So supposing that we have that the suspension of AJ is in W, so is a wedge of spheres for all J, what we really need to ensure that our polyhedral loops on our polyhedral product on the polyhedral joint product belong to P is that loops on the polyhedral product on M belongs to P, so what we started with belong to P. Loops on the polyhedral product associated to Ki is in P for all I. And we need that the suspension of these HIs belongs to W for all I as well. So that HI was the map from the polyhedral product on Li into the polyhedral product on Ki. So we need that to belong to P. Yeah, I'm not going to go through a proof, but I thought I might do an example to show how this works. So here we're going to go back to our previous example of a substitution complex. So we're going to let M be the boundary of a 2 simplex. We're going to let K1 and K2 be vertices, and we're going to let K3 be an edge. So that was our substitution complex. So we already know that the polyhedral product on the boundary of a simplex is going to have a loop space in P. And for all of our Ki's, we know that that's kind of trivially going to be true. So here we're only really going to worry about our HIs, which are here. They're the homotopy fibers of these maps. But these maps are all null homotopic. So we can kind of easily determine that if the suspension of our AIs belong to W, we're going to get that the suspension of our HIs also belong to W. So we know that the loop space of the polyhedral product associated to this substitution complex is going to belong to P. And this actually holds far more generally for substitution complexes. So the substitution complex was the polyhedral product on the pair K and the empty set. So in this case, HI is going to be the homotopy fiber of including this product of AJs into the polyhedral product on KI. It's known that this map is null homotopic, and so we're going to get our HI is homotopy equivalent to this product of AJs times loops on our colon AA KI. And given conditions on this that guarantee that it belongs to P, and given that we've assumed that suspensions on all of our AJs belong to W, you can see that after suspending, this will always be in W. So yeah, for the substitution complex, we no longer have to worry about whether our HIs or the suspension of our HIs are still wedges of spheres, because we will always get under these conditions that our HIs are wedges of spheres. So we only need to worry about loops on colon AA being in P and loops on colon AA KI being in P. Okay, this is enough to kind of create new examples of simplicial complexes that produce moment angle complexes with loop spaces in P. So there are 4, just to recall, there are 4 cases that are known. When the underlying moment angle complex is a wedge of spheres, when K is the K skeleton of a flag complex, if K is the triangulation of S2 or S3, or if K is a 2-dimensional simplicial complex up to some other conditions. So the last 2 ones, we can kind of dimensionally move away from that. The polyhedral join products are very large. They get very large very quickly, so we don't have to kind of worry about that too much. And it's really the first 2 conditions that we have to be careful with. So how can we guarantee that our substitution complexes aren't going to fall into either one of these categories? Well, to start with, we'll deal with the case where the moment angle complex associated with our substitution complex belongs to W. So if we have a full subcomplex of K, then the polyhedral product on that full subcomplex retracts off a polyhedral product. So we had that list of all the full subcomplexes of the polyhedral join product, and in particular the substitution complex. So here, all we need to do to guarantee that our moment angle complex won't be in W is guarantee that either our starting complex didn't produce a moment angle complex, but it's homotopy equivalent to a wedge of spheres, or we make sure that we're substituting in at least one thing such that the moment angle complex associated with that is not homotopy equivalent to a wedge of spheres. Then because we'll have that retracting off, and we can't have something that isn't a wedge of spheres retracting off something that is a wedge of spheres, our moment angle complex associated to our substitution complex will not be homotopy equivalent to a wedge of spheres. Our second condition was K skeletons of flag complexes. And here you can almost always guarantee that your substitution complex isn't going to be the K skeleton of a flag complex. But here I've just done it for when our starting simplicial complex isn't a flag complex. So if we start with M being a simplicial complex that is not flag, if we substitute something into a minimal missing face that at least has a edge, we can guarantee that the associated substitution complex is not going to be the K-skeleton of a flag complex. And this comes from the fact that if you substitute something with an edge into a minimal missing face, you preserve that minimal missing face, but you also introduce faces that are of the same dimension. So you have missing faces and filled-in faces of the same dimension. And so you can kind of guarantee it's not going to be a K-skeleton of a flag complex. So this is obviously a kind of two-dimensional example, but in the interest of illustrating kind of the work, I thought I'd go through this one. So here we're going to let M be the boundary of a two-simplex. We're going to let K1 and K2 be vertices, and we're going to let K3 be the boundary of a square. So it's going to look something like this, where all these faces on the outside are filled in and all these faces on the inside are empty. So we're first going to show that the associated moment angle complex doesn't belong to W, but K3 is going to be a full subcomplex of that substitution complex. And we know that's a product of two three-dimensional spheres. So we get that that moment angle complex is not going to be a wedge of spheres. We also want to show that it's not the K-skeleton of some flag complex. So, 1, 2, 3, our boundary of the two simplex is the minimal missing face of M. And we've substituted in K3, which contains an edge. So by our previous lemma, we're going to get that's not the K-skeleton of a flag complex. However, you can just kind of see it from this, right? We know we're going to have missing faces of dimension 2, and we've got filled-in faces of dimension 2. So it just can't be the K-skeleton of a flag complex. And then finally, because we want to move away from these two-dimensional, three-dimensional examples, I thought I'd end on the generalization of that. So if we let M be the boundary of a simplicial complex on M vertices, and we're going to let each Ki be an eigon, then from our theorem 1, we end up with this loop space homotopy equivalence for the moment angle complex associated with that. And we know that this is going to belong to P by our previous corollary concerning substitution complexes. We know that loops on the moment angle complexes associated with our P and eigons are going to belong to P, and we know that it's well known that this is going to belong to P as well. So we get that the moment angle complex associated with our substitution complex will belong to P. We get that these are new examples because the substitution complex here is not going to be the K-skeleton of a flag complex by the previous lemma, because we've substituted something with an edge into the minimal missing face. And the moment angle complex associated with the substitution complex is also not going to belong to W, because we've got all of these P and eigons retracting off it as full subcomplexes. And we've already seen that they have the homotopy type of a connected sum. So these are kind of a family of new examples of simplicial complexes that produce moment angle complexes with a loop space in P. And I think I'll stop there.
Could you show the slide where P is defined?
Yeah.
Thank you.